Good morning, this is David Johnson. Today I'd like to show you the project sizing form. This is where we do probably 80% of our work in Hypersizer, so it's very good to review this form. For this example, I'm going to look at a honeycomb sandwich simply supported beam. So what we have here is 2 face sheets and a core. Right now what I've set up for optimization of these face sheets is 15 steps from 0.01 to 0.08. A little impractical, but I'm just trying to show the example here. The core is 2 inches. We have to be careful optimizing the core in Hypersizer. If we use the fen method, we have to make sure we loop around to change the model with the depth. But if we do this manually with no fen loads, you can optimize the core within Hypersizer. And the bottom skin is 0.01 to 0.08. We have 2024 face sheets and we have a titanium honeycomb core here. As you can see, I've asked for only one design. We can ask for many designs, and these options provide 225 candidates. So when I do an analysis, Hypersizer looks at all 225 candidates and finds out which is the lowest weight, which you'll find the weight here. So if we do the analysis, which is a little slow because I have the screensaver running to record this program. So if we run the analysis, which was already run, we end up with 30 thou 2 face sheets, and obviously I didn't optimize the core, so the 2-inch core. One of the things I should have checked prior to the analysis I'll turn these off for a second just to show. First thing I should do is check how many components I have in my fan. In this particular example, we have a 16-inch long beam with 2 simple supports and a load in the middle. We have 1 thickness in the middle here and a thickness for the 2 ends. Now this is where you, the stress engineer, you play God when you do optimization, because you have to decide how many components or how many different thicknesses you would like over this span. Now manufacturer may decide that they only want 1 thickness and it has to be just 1 uniform thickness, in which case you just optimize the middle element here and you're kind of done. And for what I've done here, I'm optimizing this component here. Also in Hypersizer we have groups which are going to be discontinued, and we have assembly. So an assembly could be all of these components. In this case, my assembly is the same as component, just because I haven't fully set the project up correctly yet. So 2 things you must check before we do the analysis. X direction. We always like the X to be span-wise, so we know what NX is. If this is inconsistent or it points the opposite direction, you have to understand those parameters. It's always best to have X in the span-wise direction. And also for the bar and beam elements, actually not bar and beam, but we're just simply showing the Z direction here. We need to make sure the Z is always in the same direction. That makes sure that the loads, if I have a plus MX, it's the same for all of these elements. So we will go back to the sizing form. So here is the failure tab. Again, we see a picture of our concept, which we actually set up here. I didn't mention that. And also you can see the assembling components from the fen viewer that I just discussed. So here we have all the analysis methods. Big topic, I'm going to save this topic for later, but what I want to say for here is all I've done is done intracell dimpling and wrinkling for the top face sheet and the bottom face sheet. I've also added a deflection limit, a stiffness limit, which is why I didn't put on the strength analysis. We could have put on the strength analysis, but if we click here, we can look under the method documentation. Again, it's a little slow because I have my screensaver running for this video. It's usually a lot quicker than this. And what we see is we can set some stiffness criteria. So what we did is we did a deflection limit, a mid-span deflection could be set up here, which is a different tab. So let's just go back and just jump forward to the Properties tab. And here you can see I've asked for a maximum deflection of 40 thou. Now the span of my beam, obviously the finite element model knows the span, but I have a problem with the screen here, but if we go to the buckling tab, again jumping ahead, I have a span of 16 inches. So if I go back to the failure, when I put in the displacement, we calculate the margin of safety based on displacement and whatever configuration we come up with here. So again, obviously I've run this already, but if you want to run it, you just simply do detailed sizing. Again, it's a little slow because my video captures using all my CPU on this computer. And as we see, as we could see before, the minimum margin is for stiffness. So we're stiffness driven here, and we have reasonably big margins for wrinkling and dimpling for the top face sheet, and for the bottom face sheet, of course, the bottom face sheet's actually in tension, so it's not an instability failure. Now let's move forward to the Freebody tab. So the Freebody tab basically is stating here that I used FEA loads. So I imported my FO6 file, and it shows the load case here. We could actually click on this button, and we could manually type some loads in here, and we could override the FEA loads if we wished. We can also, let's just go back, we can also put the length in on this form too. There's a couple of different places to put the length of the beam in. So I have a length of 16 and so this shows both lengths, but it's a width of 1. I have clicked here an initial imperfection of 0.30 thou. I usually do that as a standard, but in this case I'm not actually doing a buckling calculation on the beam, a compressive buckling, so this number wouldn't be used. And we also have the option of putting panel pressure on here, but there's some issues as to whether you can apply panel pressure with FEA loads. I actually forgot. I think you need to use user loads, but that would be an advanced topic. So this form doesn't really have much to show if you're using FEA loads. Now let's step to the stress tab. Again, we see the load case, we see the top face, core and bottom face, and we have loads NX, NY, and XY, which we're all familiar with, MX, NY, and MXY. And one thing I didn't mention earlier is the temperature of the analysis. Perhaps that should be another topic. But this temperature that I set up earlier on defines how we calculate the margins of safety and what allowables are used. And below we have the average stresses. So in this case we have 54 KSI on the top, and the bottom face we have 63 KSI. So perhaps I should have turned the stress function on. We also just have my screen's not showing the whole sheet here, but we just have basically this is actually for BGSFM partly, but this shows the load convention. If we have local pressures applied, and this is for BGSFM, which we'll show at some other point. So as we can see, as we'd expect, these moments are not the drivers. The real driver is NX in the minus NX in the top sheet and minus and plus NX in the bottom sheet, which is what you'd expect for a cantilever beam, and we're looking at the middle elements. So the moment is a design driver. If we now step forward to the buckling tab, you can see I've set up the span length, I've set up the width 1 inch. A buckling knockdown factor, sometimes at some aerospace corporations we have a knockdown for buckling, some places as high as 2. But just be careful with Hypersizer, because this factor is the opposite way around, so it's 1 over our knockdown factor. You can see here that I've put in simple supports. We'd use this if I was doing some buckling analysis, which we didn't do, and 3 on the 2 edges. If I scroll down, you can see we can put in curved beams and put the radius in if desired. In this case we've got a flat beam or a full cylinder. And also we can do some post-buckling analysis, which is too detailed for this particular initial lesson. If we then go to Properties, the Property tab is a location really where we set up our stiffness criteria. For instance, if we're using composites, we can put in the axial and bending term A11 and the D terms, D33. And you can see we can put in some natural frequency requirements, which is pretty good. And we can limit the strains. And also in my case, as I've done here, we can limit the mid-span deflection, which is often, when we design things, displacement quite often is a design driver. You can see here that we find the neutral axis, so Hypersizer calculates a neutral axis, and it also calculates the ABD matrix. We also have some thermal coefficients here, which I've not gone into. The Options tab, not too many things here that I not often use. We usually use the mid-plane analysis. The 2 things that are important here is we've got some wrinkling coefficients. These 2 are pretty standard in the aerospace industry for doing our wrinkling analysis, but if you need to change these 2 or correlate your analysis better with the test, you can change these numbers. These items here, adhesive, if we're doing composites and we have a curved panel, we can put some information here to calculate the flat-wise tension, which is pretty important. F33 is always a big design driver for composites, and something most engineers forget about this important failure mode. In this case, in today's example, we're not actually calculating any flat-wise tension. So I'll go back to the dimensions. This is really where you set up the real example of what you want to look at, and as I said before, the analysis shows we needed 035 skins on the top, 2-inch core, and 030 skin at the bottom. A simplistic example, but the whole objective really was just to show the basic principle of how Hypersizer works. So this kind of methodology, depending on what concept you choose, it's a little different. But for honeycomb structures, it's pretty straightforward. I think it's actually very powerful. There's very few packages that actually allow you to do what I'd call real analysis, which is, this is really hand analysis, P over A and Y over I, buckling, callus, whatever we've got in here. These are doing the hand cranks that we do manually, and it's pulling the FEA data in to do automatically. So if you set all this up, this can be very powerful. So thanks very much, and have a good day. That's the end of this tutorial.